today go through the clock analysis theory as well as the solutions that we bring to clock analysis. And so, like everybody knows, the clock is one of the prime electrical signal in any system, any high-speed system. And the way we actually go about the clock analysis is very different from the other vendors that we have. And so I will go through those features which we provide. And there are two very critical components in clock analysis. One is the jitter, which is more of a time domain measurement tool, and the other one is a phase noise measurement. So in earlier days, whenever you want to do a phase noise measurement, you would rely on a different equipment, which is mainly a spectrum analyzer or a phase noise analyzer. But today, with all the computing power which is enabled within our oscilloscope, we are able to do the phase noise analysis within the scope itself. So you get both the jitter measurement, which is a time domain measurements, as well as the frequency domain measurement, which is more of a phase noise measurement. So with this having said, it becomes a very powerful tool for you to analyze within one equipment itself. So you would know the relationship between the timing measurement as well as the frequency measurement, so with which you can analyze your clock much more effectively. Like I said, clock is in the driver's seat all the time, and any embedded board you take, whether it's low speed or high speed, a clock is a must within an embedded board. So which all the synchronization that happens within a system is based on that clock. And if the clock is unstable, then anything and everything does not work. So that's why the clock is more important to analyze before you analyze any other signal in your board. So having said that, I would just tell you what is the agenda for today. So we would cover the jitter measurement in time domain, which is mainly around the oscilloscope that we have. And the other two, which is again pertaining to the measurement, would be the spectrum clocking, which is more of a compliance because of the EMI and radiations that is emitted by these electrical signals, and they have to be within a particular threshold for which the spectrum is always a part of the clock. And then we have the other timing measurement, which is called the accumulated jitter measurement, which is more of a periodic jitter measurement. And then the other part is the frequency domain measurements, which is a phase noise. And then we have the relationship between the clock jitter, which is in the time domain, versus the phase measurement with the frequency domain. And then we also have a correlation between the clock jitter in the time domain as well as in the frequency domain. Then I would show a live demo. Maybe I would also go, as I go through the slides, I may have a demo coming up so that it becomes more interactive, seeing the theory as well as the menus that drives the clock analysis, as well as the actually signal which is is enabled through the the lab notebook that we have, which enables us to actually have a simulated signal coming up on the scope screen, and then you can actually do post analysis on it. And then I open up for question and answers. And as I go through, you can also, put your questions in the chat box, and we would answer all these questions at the end of the session. So, like I said, there are two main, parameters that we are going to measure. One is the clock jitter in time domain, and the phase noise in the frequency domain. Now, if you take a clock, the clock has an edge which actually determines when and everything has to happen time synchronized with this edge. For a simple example, if a person is writing a Python code, the Python code is at the top layer of any software application. But down the line, there are many layers, which is both could be in hardware as well as software. But at the grassroots level, these are executed in a form of assembly language, or opcodes we call it. So, for example, if you take an edge, the edge determines when an opcode has to be fetched from the memory. And once the opcode is fetched from the memory, the next execution is to actually decode the opcode. Third would be to execute the opcode. So in 3 edges, the entire operation happens. And that's the reason why the edge or the clock becomes very important for any analysis. So like I said, the clock has to be analyzed in all respects, in both in time domain and frequency domain, for you to make sure that the system works very stable and without any errors as far as the BR is concerned. So going down the line, we see that the jitter is one of the main, issues that can arise because of many factors. And as I go through the slides, you will see why we say that. And so to bring about all these, the measurement tool, we have an oscilloscope, which is a 12-bit oscilloscope, which allows you to make very accurate measurement of your electrical signal, because having a 12-bit, true 12-bit makes it a very, very, measurement accurate instrument. And we have a depth of, in terms of the record length, that we can capture a very large capture time, which is about 8 gigapoints of data, which means if you want to look at a low frequency jitter, you need to have a capture time at least one period of the capture time. So which means then you can see a low jitter value as well as a high jitter measurement in the same acquired waveform. In general, though we have an 8 gigapoints of data, but the analysis memory, which is part of the analysis of your waveform, is only at 500 megapoints. So any scope vendor, though they give you a very large memory for capture, will have a limited analysis memory, which is called the post-processing through the DSPs that we have in the scope, and that would be limited to 500 megapoints. And 500 megapoints is still a huge number, because if you look at all the the protocol standards that we have in the industry, like the PCI Express, USB, or any of those standard protocols, still has only 32 million points as a compliance capture time. And so 500 million points is about more than 10 times the value of the normal standard compliance requirement. So we would be able to give you a much better, analysis of your signal in a much better way, because you're also looking at the low jitter values with at a low frequencies. And all our screens, which we have, is a very flat display, we call it as, because everything that you set up in terms of the waveform, in terms of measurement, or in terms of all the graphical representation that you have, in terms of histogram, in terms of TIE, which is nothing but the time interval error, which is tracked by the waveform, everything comes up as in multi-grid display, and which makes it a very, very informative as far as the wealth of information that you get for a particular signal. Here it's a very simple signal, which is nothing but a clock, but then the derived values from that raw data is much, much more for you to make a very, very in-depth analysis of your signal. And if you look at the measurement values that we represent, statistic and probabilities are the two main mathematical functions that go with any raw data. So the more the statistical information and the probability density function that we have allows you to analyze your signal much, much clearer and get a clear picture of your signal. And you can debug them by just looking at those graphical representation. And we are very powerful in terms of the histogram that we call it as. And under every measurement that we have something called a histocon, which is nothing but the distribution of the statistical information that we gather over a period of time. It could be on a single acquisition or it could be on a multiple acquisition, but these histocons represent the distribution of your parameter over time. And these are very, very important, because if you look at the final end result of your jitter values, these are all derived from the histogram. So the more the population that you have and the more acquisition that you have on the histogram in terms of the values that is being populated into the bins, and that makes it more effective way of analyzing a signal. And we are the only ones to give you a histogram with 2 billion values and up to 5,000 bins, which means you will have a continuous raw data information within the histogram for you to analyze it very, very well. And as you know that the histogram shape becomes a very critical analysis tool visually. And so the more it is Gaussian, or we call it as a normal distribution. When it's a normal distribution, then you know that the signal that you're measuring is to some way more natural in nature. And so you will be able to make any correction that is required. But any abnormalities, single, and the shape of the histogram is different. It could be non-linear, it could be bimodal, or it could be of any other shape. Then you know that you are in trouble. And so histogram is one of the most primary display that we always request customers to look at, because that is what is a fundamental distribution that you get for all the parameters that you are trying to measure. And further which, we also have all the measurement tools like the jitter measurement tool as well as the eye parameter measurement along with the eye diagram to make it a complete seal data analysis tool along with the clock analysis tool. Now, earlier in the earlier days, we used to have the clock as part of the seal data analysis tool, but over time we have removed the clock and made it a separate, option, because it is becoming more and more complex to make clock analysis because of the requirement of the the speeds at which today all the memories and data is acquired from different sources.